So one of the things that we've encountered in this unit so far is occasionally we come into an equation, we run into an equation where the unknown is part of the exponent, and all we've said is the only way you know how to solve that equation for that unknown is by graphing it. There are other ways to do it. One of the ways to do it is what we're going to look at today, but this method doesn't always work. Okay? This is really important to note, that once we learn about logarithms, we're going to come back and look at solving exponential equations, and we'll use a method that will always work later on. This method we're going to use today doesn't always work. We're going to be solving exponential equations under a very, very specific condition. It's when the bases of all of the powers can be expressed as what we call a common base. For example, just jumping ahead here, if I take a look at this equation, there's two bases. There's a power on the left with a base and an exponent. There's a power on the right. Well, there's a base. I guess the exponent is 0, or pardon me, the exponent is 1. But both of these bases, 3 and 81, can be expressed in base 3. Because 3 can be expressed as 3 to the 1, and 81 can be expressed as 3 to the 4. If you figure out what 3 times 3 times 3 times 3 is, you get 81. So my point is that 3 and 81 have what we call a common base. Those obviously have a common base. The common base is 7. The common base here, with a little bit of thought, well, maybe it's 36. Maybe we can take 36 and raise it to an exponent and get 216. And you might try that. You might try 36 squared. But that doesn't work. So how else could you express 36 as a power? Well, it's 6 squared. Is 216, everybody, a power of 6? What I'm asking is there a whole number that we can raise 6 to get 216? The answer is yes, it's 3, right? So these two things have common bases. We can solve these equations that I've shown you so far using what we're going to learn today. That one we'll get to. I don't want to get too far off track. This is an equation where there's no common base possible. So the method we're going to look at for solving this today is kind of a clunky method, but later on when you know about logarithms, you can come back and you can solve this exactly. All right, so going back to the objectives, if the base can be expressed for everything as a common base, we're going to use a particular method. If it cannot be expressed, then we can do one of two things. We can solve them graphically, or we can solve them using kind of a trial and error, which is a very, very clunky method. Okay, we'll get to that. And then what we're going to do is we're going to continue to work with that y equals a times b to the t over p, and we're going to apply it to what's called compound interest. So to begin with, an equation like 2 to the x equals 32 is called an exponential equation because the variable appears in the exponent. This is what makes a function exponential. There's an x in the exponent. This is what makes an equation exponential. There's an x in the exponent. By the way, this is a laughably simple equation for you to solve, and it illustrates an idea here that when we do what we do today, at some point, you're not going to do algebra to get an answer. You're simply going to ask yourself, what is x? What do I raise x to? Pardon me. What do I raise 2 to get 32? What would I raise 2 to? What exponent would I raise 2 to get 32? 5, isn't it? So 2 to the 5. So there's no algebra here involved in going from here 2 to the x equals 32. Just simply saying x equals 5. And our goal is always to boil it down to that initially so that we can solve things algebraically. Okay. So let's solve this equation. Solve for x by using a common base. 7 raised to the 4x minus 5 equals 7 raised to the 2x plus 3. Well, anybody tell me why this must be true? They're the same base. So the idea here is, like Patrick said, they're the same base. So if I have 7 raised to an exponent, and I'm saying it's equal to 7 raised to an exponent, the only way these two things can be equal, is if these two exponents are exactly the same, right? So I want to make a point here. It's not that when we go from the question to what I've written in brown that we divide both sides by 7. That's not what we're doing. If you divide both sides by 7, that's not what you get. You get something different. What we're doing is we're simply saying if the bases are the same and the powers are equal, then the exponents must be equal. And this is changed into a grade, well, it's a junior high question. And that's being generous. Okay? So I can subtract 2x from both sides and get 2x on the left. I can add 5 to both sides and get 8 on the right. I can divide both sides by 2 and get x equals 4. And if you like, you can check that by putting 4 back in for x. If I put 4 in for x on the left, I've got 7 to the 4 times 4 minus 5. If I put if I put 4 in for x on the right, I get 7 to the 2 times 4 plus 3. On this side, I get 7 to the 11. Here, I get 7 to the 11. This maybe illustrates an important point. I don't think we need to figure out what 7 to the 11 is. It's obvious that they're both 7s, they're both 11s, they're both equal. So then, what do we do in a case like this? Well, you look at it and you recognize that there's a common base. I would like to make a point here, though. When you learn about logarithms and are able to solve this algebraically in a different way, I still would use the method that we're learning today. Anytime there's a common base, don't use logarithms. Even though you don't know what that would entail, just do what we're learning today because there's a common base. I can write this equation as 3 to the 3x plus 1 is equal to 3 to the 4, that's 81, raised, well, I guess we don't really need to say raised to because the 81 wasn't raised to anything. This again is a very simple equation. As soon as you see that 3 to the 4 is 81, then that must mean that 3x plus 1 is 4 because the bases are the same. It's a comparison. Again, very simple to solve now. 3x equals 3. Divide both sides by 3, you get 1. Any questions with A or B? Good. C. Again, we already talked about this, but I would like to go through it in more detail. Perhaps the common base is 36. Maybe you're looking at it, you're saying, well, you know, in this question, the common base was the smaller base. I could take the smaller base and raise it to an exponent to get the bigger base. When you do that here, if you were to take your calculator and take 36 squared, I don't know what 36 squared is, but I do know that it's more than 216. And at that point in time, you realize that 36 is not the common base. So my advice is go with the smaller base and ask yourself if you can take that smaller base and write it as a power. A power is a base raised to an exponent. Well, we could write it as 36 to the 1, but that's not helpful. So is there any other way to express 36? Well, 36 is 6 squared. So as soon as you see that, then you suspect that 216 can also be expressed as a power of 6. And you go to your calculator until, and you may not get to this point, but until you get really familiar, after a while, many of you will know 216 is 6 squared. You'll see it enough times. Pardon me, I just said squared, didn't I? 6 cubed. So we get 6 cubed. Now, what do we do with the rest of this? Well, this 36, everybody, is raised to the 2 minus 3x, and this 216 is raised to the x. And that set of brackets is important. These are each what we call, I don't like what it's called, but it's what we always call it, a power of a power. And a power of a power, just to go back to grade 9 math, if I had p squared cubed, what that is p squared times p squared times p squared. And if I really want to boil things down, that means this, because p squared is p times p. And if we count the p's, there are 6 of them, so we end up with p raised to an exponent of 6. But the shortcut is simply to say when you have a, quote, power of a power, you multiply the exponents. You don't add them, you multiply them. So what that means is this becomes 6 raised to the 2 times 2 minus 3x. This becomes 6 raised to the 3 times x. And now what you have, and I'm going to come back to this idea many times. I guess if I could summarize what we're learning today, it's that when you have a base raised to an exponent and it's equal to the same base raised to an apparently different exponent, those two exponents have to be equal. I mean, they may look different, but they have to be equal. So this is the main gist of what we're learning today so far. We can drop the bases here, or we can simplify the exponents here and drop the bases later. It doesn't matter. I'm going to keep the bases in and multiply this out to get 4 minus 6x equals 6 to the 3x. Well, now we can drop the bases and say 4 minus 6x is equal to 3x. And again, there's that philosophy that I've adopted, which is to turn difficult questions, questions you learn in grade 12, into questions that, in this case, we can do if you're in grade 8. It's not that difficult. You know, the way you would explain this or justify it in grade 8 would be different. You'd probably write plus 6x. Here we're a little more finessed. We can just say I'm going to add 6x to both sides and get 9x equals 4. So x is equal to 4 divided by 9. Watch how you divide here. Sometimes when you have your x's on the right-hand side, people divide backwards for some reason. They go 4 over 9. They don't go 4 over 9, they go 9 over 4. Okay. Any questions with that one? Well, I'm perfectly aware that many of you could go from this line directly to this line, and that's fine. I think on a written response you should show at least another layer in there of something. Okay. I'm perfectly aware that many of you could probably go to that bottom line by just looking at this equation and saying 36 is 6 squared, so I'm going to multiply that exponent by 2. 216 is 6 cubed. I'm going to multiply that exponent by 3 and put them equal to each other. You have to show your work for written response. Let's try one more. 5 to the x equals 625 root 5. Very basic question. These will get more complicated as you'll see today. But given that the left-hand side is 5 to the x, and 5 is a prime number, it doesn't even have any other factors other than 5 in itself. We can't write 5 as some other base to an exponent. That's telling us the common base must be 5. So your job now is to go to your calculator and determine what 625 is in base 5. And you know that it's not 6 squared or 5 squared. 5 squared is 25. What is it?
5.
Is it 5?
Yeah, 5 to the power.
5 to the power of 5? Are we sure about that? Just double check.
5 to the power of 4.
I think it's 5 to a 4.
Yes, it's a 4.
Because 5 times 5 is 25. 25 times 25 gives 625. So it's 5 to the 4. So we end up with 5 to the x equals 5 to the 4, and then we have root 5. Well, what you learn in earlier grades, I think you officially learned this last year in grade 11 math, but your math 10 teacher probably talked with you about it, is that when you have a radicand under a square root sign, that's exactly equal to a power expression where the radicand becomes the base and the exponent is 1/2. And that means that something like root 5 is 5 raised to the half. And we're pretty much done except for one more thing. And this goes back to grade 9. When you have a power of a base s times a different power of the base s, this is equal to the same base raised to an exponent of the sum of those exponents. You don't multiply s times s, right? There's a tendency here looking at this equation to see 5 to the 4 times 5 to the half and think 25. Because you see 5 times 5. We're not multiplying 5 times 5. We're multiplying 5 to an exponent times 5 to another exponent. So we add the exponents, and now we're pretty much done. Because then you can see that x is equal to 4 plus 1/2, or 4.5, or 9/2, however you want to write that answer. The purpose of these examples is not to demonstrate exam questions to you. Even this one, although it's got radicals in it, is not rising to the level of an exam question. If we were to take a look at some of these questions here in number 5, those are certainly rising to the level of a Math 30-1 question. There's more in them. There's more on your shoulders to be responsible for. But the basic steps are going to be find a common base, convert everything to the common base, set the two exponents equal to each other. And the more practice you get, the easier they will become. So that's just the first part of the lesson. I guess we got one more, example 2, but we do not have a common base. So we're going to solve this using what I call systematic trial and error. And then we're going to solve some equations using graphing. And you're going to understand very quickly that it's a fine line between the two ways to do it. Solving graphically, solving by systematic trial and error, same basic idea. So what is the basic idea behind trying to find an answer here? It's saying that 3 raised to some number gives 25.8. Now, I happen to know that 3 squared is 9. Well, that's not 25.8. And I know that 3 cubed is 3 times 3 times 3, which is 27. So the reasoning is that if 3 squared gives 9 and 3 cubed gives 27, then there will be an exponent here that is between 2 and 3 that will give you 25.8. Because as the exponent goes up, the power goes up. So I think your textbook kind of leads you down this path that what you start doing is putting in values for x. And that's fine. We could try 3 to the 2.5. Not quite there. I'm a big fan of using my tables. So I'm going to put in for y 3 raised to the x. I'm going to change my table setting to automatic. I'll show you 2 ways to do this. Automatic, and I'm going to start at 2, and I'm going to go up by 0.1. This is going to create a table that has 2, 2.1, 2.2, 2.3, etc. So when I go to my table, make sure I've entered that correctly. I go to my table, I'm looking for what? 25.8. Well, now I can use the same reasoning that I had before. I reasoned out that it was between 2 and 3, and now I can see that 2.9 gives 24.19, which is too small. 3 gives 27. It's somewhere between 2.9 and 3. So what I can do is reassess my table setup and start at 2.9, and this time go up by 1/100th, 0.01. And I hope you would agree that this is a clunky method. You understand what I mean by clunky? It's not very efficient. It will work. So now we can see it's someplace between 2.95 and 2.96. So we can start at 2.95 and go up by 0.001 if we want. Let's just do it one more decimal. What did I say? It was between 2.95 and 2.96. So this time let's go up by 1,000th. Except I want to start at 2.95, which I don't think I changed. I mean, that's as close as we can kind of get. The answer is about 2.959. Are we okay with that? Now, if you knew about logarithms and you knew some procedures for logarithms, you could take the logarithm of 25.8 and divide by the logarithm of 3 and have absolutely no clue on why this is going to work or what this is doing, and it turns out that this is the exact answer. Okay? If I were to take 3 raised to that, I don't get around 25.8, I get 25.8. Don't try to memorize that procedure because it's going to be different depending on the equation. Let's try another one. So it wouldn't work here. There's more involved here. Again, I'm going to go to my calculator. I'm going to enter in the variable side of this equation, which is 1.5 raised to, in brackets, x minus 8. This is not necessarily always the best approach, but it's a starting point. Start at 0 and go up by 1. We can reassess later, but now when I go here, I'll just double check it's entered correctly. Now when I go here in my table, I'm looking for y1 to be 12, and I can see that I probably have a fair ways to go here. Well, not so bad. I don't have to scroll very far to determine it's between 14 and 15. So now I can narrow things down. I can start at 14 and go up by 1/10. I can start at 14 and go up by 1/10 and go to my table. I'm looking for 12. Well, now I see it's between 14.1 and 14.2. So I can start at 14.1 and go up by 100th this time. I think you get the drift here. I would say 14.13 is pretty close. Okay. So x equals 14.13-ish. You know, again, if you knew about logarithms, and you wouldn't, I don't think many of you will graduate to the point where you can just do this on your calculator. You would have to show some work to understand what's going on. But I'm doing this to illustrate to you that there will come a time where we don't have to do this. What do we have? Log of 12 divided by log of 1.5 and then add 8. This is the actual answer. And again, if I were to take 8 away from that and raise it as an exponent on 1.5, I would get exactly 12. All right, solve graphically. Well, the issue here is coming up with the window settings, but we're going to use our tables to determine window settings. First of all, you should know that this function, y1, will have a y-intercept of 1, and it is a decreasing exponential function. You should have a vague recollection of that. Well, not even vague. You should know it. Right? Y equals 12, on the other hand, is way up here somewhere. So we know they're going to intersect someplace on the left-hand side of 0. Well, my thinking is I'm going to enter y equals 12 and y equals, what do we have, 2/3 in brackets, raised to, in brackets, x over 4. Before I graph and before I change any window settings, I'm going to go to my table to see about where it is. And I'm going to start at 0 and go up by 1 automatically. This table thing, once you wrap your head around it, is brilliant. So I can see if I increase x, these numbers are not getting closer together. I'm getting further away from 12. So I go in the other direction. And if I get tired of scrolling, then I can go and have a different start point in my table setup. But I think it's going to start exploding here soon. Well, not exploding, that's an exaggeration. It's around -25. So I'm thinking, if you look at my hands, if we go from -27 to -23, that's probably good enough. So window, -27 to -23. I don't need to go up to 100. I need to go up to at least 12. And I'm telling you, if you don't explore the values in your tables, it becomes very frustrating in trying to find out where they intersect. If I've done things right, I should get a pretty decent looking graph. It shouldn't be really steep. It should be clear. I should be able to see both functions. And now I can find the intersection point. You know, of course, you could have solved any of the ones in example 2 using this. Instead of just clunking around in your table, you could have done the graphical approach. This is approximately -24.5. And again, there's a way to determine an exact value on your calculator or on paper. Let's do one more of this type of thing. So the numbers are really big here. We have 75. Well, we're just going to do this as y1. We're going to do this as y2. And you know, this is kind of like trig in a sense. You can't look at that and just freeze and go, oh, look at 75 for a base. Wonder what that's going to look like. Don't worry about it. Put it in. So I have 75 raised to, in brackets, 2x minus 3. Let's clear all this other clutter. And I have 2.5 times 3 raised to the x. And we're going to go to our table. And we're going to start at 0 and go up by 1. Let's just explore things that way. Go to my table. And I hope you understand this. 2.4 times 10 to the negative 6 means 0.000000 and then the 2. 0.4, or the 2.4. So there's 5 zeros and then the 2. It's a very small number. And if we take a look, I know that most of you should get this without any problem. If you take a look here, when x is 0, y1 is smaller than y2. And when you take a look here, y1 is still smaller than y2. But all of a sudden, when you reach this point, y2 is bigger pardon me, y1 is bigger than y2. They've switched. And if you think of things graphically, the only way y values can switch is if the graphs cross each other. So we're looking at a solution here someplace between 1 and 2. So you go to your window setting. You go to your window setting, not the table setup. You go from, well, let's go from 0 to 3. I don't know. Somewhere between 1 and 2. 0 to 3 will do the trick. We have to go up to at least 75 so we can see it. I'm going to go up to 100. Again, if you graph it and you've done things properly rather, you're going to see a nice picture to deal with. If you went zoom standard, it wouldn't even be clear where the intersection point is. Or zoom in or zoom out, it just doesn't go anywhere. So we can calculate this now. And the answer is approximately 1.84. You know, again, approximately. Any questions with that set of examples? By the way, I mean, we did use a bit of knowledge about exponential functions for these. Don't forget, everything we did in example 2 and 3, you could basically do with any equation. Any equation. Exponential, logarithmic, trigonometric, quadratic, cubic, anything. All right, now we're going to look at one more application of exponential growth, which is compound interest. So when money is invested, the interest earned is almost always earned in a compounded fashion. What that means is that, let's just say I was living in an amazing world where we had 10% interest. And it doesn't matter when they calculate it. Let's say it's every month, which is a utopia. You just throw your money in the bank and you become rich overnight. Or, well, monthly, you'll become rich. So these ticks are going to be months. If I put in, let's say I put in $5,000 into an account, then 1 month later, I'm going to have $5,500. Just give some thought as to how I got $5,500 there. 10% interest means the bank takes my money and they keep it for me. I'll tell you what they really do with it in a second, but they take my money and they keep it, and at the end of that month, they give me 10% as a reward. Thanks for letting us use your money. Okay? But compound interest means when I wait 1 month later, I don't earn $500 interest. I earn $550 interest because now it's 10% of a bigger amount. So what I would end up getting is, how is my math there? Is that right? If I take 10% of 5,500 and I add it to 5,500, okay, and you can see what's happening here, by the way, is I'm multiplying by 1.10 because I'm increasing by 10%. It's like the population things we talked about. If it goes up by 10%, then it becomes 110%. So what happens is, if it were what we call simple interest, this is what the graph would look like. Every month you get a certain amount. What it looks like, though, is this, and that's exponential growth. Okay? How can the bank afford to give me 10% of that? Well, the answer is they borrow the money from me, and then Ali borrows the money from them, and they charge him 15% interest. It's a bit of a scam, really. I mean, they're taking somebody else's money and giving it to somebody else and charging them more than they give you. So when interest is calculated as a percent of the amount of interest is added to the account, and then next time you get more interest. Do you get the basic idea here? Okay. That's exponential growth. So we're still using this formula, okay, but it's going to be a little more complicated. In this formula, y is the amount of money and t is the time. I would prefer to work in years because interest rates are usually given per year, and we'll talk about that in a minute. Y is the time in years. P is the length of time it takes for us to get interest. So listen, If you're getting interest annually, P is 1 year. If you're getting interest semi-annually, P is 0.5 of a year. If you're getting interest monthly, P is 1/12 of a year. It's the length of time it takes for them to give you interest. And A, of course, is your original value or original amount. So let's take a look at this example. Jerry invests $10,000 in an account that pays 8% per annum. The word annum means annual or year. From now on, if you see the word annum, it means yearly. It's compounded annually. What does that mean? What it means is if this represents 1 year, and this is January 1st, and this is December 31st, you put your money in the account, and that money stays in the account at the value that you had invested, and then on the last day, it goes up. And you earn a certain percentage of the whole amount. And the percentage is 8%. So how much is in the account after 14 years? Well, A is $10,000. It's the amount of the investment. It's the initial amount. If you were to look at this on a graph, the graph starts at whatever that value on the y-axis is, which is the initial investment, 10,000. Then we have B. If it's 10%, if this little thing here is 10%, and this was 100% of the investment to begin with, then you have to multiply 100% by 1.10 to get 110%. Or you could say B equals 100% plus 10%. So B equals 110%. But percent means divided by 100. So you take 110 divided by 100, you get 1.10. Raised to the T over, what is P? P is the length of time it takes before the money gets multiplied by something. It's 1. It's 1 year because it's annually. So this is our equation. And I don't know why I wrote A there. I should have written Y. So this is our equation. Y equals 10,000 times 1.08 raised to the T. That's it. So how are we going to find out how much money is in the account after 14 years? We're going to put 14 in for T. That's it. That's all we need to do. So 10,000 multiplied by 1.08 raised, it was 8%, wasn't it? Raised to the 14. $29,371.94. That's the amount of money in the account after 24 years. 14 years. And by the way, 8% interest. You're not going to get 8% interest on any kind of reasonable investment. It was 1982. You might be getting 14, 15, or 20%. If you played with your money properly, in the late 70s and early 80s, you could become a millionaire over a very short period of time, like 10, 20 years. Then again, a house had a mortgage rate of 28%. So it was a trade-off. What's the other part of this question? The other part of this question is how much interest is earned. Well, 19,000 $371.94. This is the interest. And I got that by saying Jerry started off with 10,000, now he's got 29,000. So it's grown by 19,000. Any questions with that example? All right. Elaine, Jerry's friend, also has $10,000 she can play with in an investment, and she puts it into an account that also pays 8% per annum, but it's compounded quarterly. Now, whenever a bank or an investment company gives you an interest rate, it will almost always be an annual interest rate. It's 8% per year. But then that compounded quarterly means you're going to get, the math is not really well thought out, but you're going to get a total of 8% throughout the whole year, but they're going to divvy it up into pieces. So it's going to be more than 8%, it turns out. But what they're saying is 4 times a year they're going to give you part of that 8%. So if we draw the same kind of graphic that we had for Jerry's investment, but for Elaine's, Elaine gets investment 4 times a year. Let's imagine that those are all equally spaced. So what's going to happen is Elaine's investment here will go up, and then here it will go up, and here it will go up, and here it will go up. And I don't know if you've noticed, but I've increased it by a larger amount each time. Not that it really matters in doing the calculation, but it will. Whereas Jerry's, he waits for a full year and it goes up, and then at the end of the next year it goes up more. And what that means is even though A is still 10,000, B is not 8%. This whole sum of percents, and again, the math is not well thought out in the financial community. It's going to be more than 8% because what's actually happening is you're getting 2% here, 2% here, 2% here, 2% here. And the reason it's going to be more than 8 is it's later on it's going to be 2% of a bigger amount. So it isn't that you're really getting 8%, you're getting a different percent. But this is schematically what we're talking about. And that means that here things get multiplied by 1.02. And this is by 1.02. And this is by 1.02, etc. In other words, B is 1.02. What is P? There may come a time where I can say to you, well, let's work in months. But I think working in years is the better bet almost always. If this whole thing represents 1 year, and I think this graphic is helpful. I hope you find it helpful. This is 1 year. A means year. Then P is 0.25 years. So what we end up with is y equals A, which is 10,000, times B, which is 1.02, raised to the t over 0.25. And again, we're going to put 14 in, but I don't want you to use your calculator just yet. I want to show something to you. What do we have? 14 over 0.25. I want you just to calculate for me what 14 divided by 0.25 is. $56? What's the significance of an exponent of 56 in this question? If we go back and we look at Jerry's investment, Jerry had an exponent of 14. So he got 8% 14 times. His investment was multiplied by 1.08 14 times, or his investment increased by 8% 14 times. The 56 is telling you that Elaine's investment, it's getting interest 56 times throughout the whole 14 years. It's getting interest 4 times as often. So now we can work this out and almost be done with it. We have one more question to do after this, though. If you're going to enter it in the way it is on the screen right now, to the left of the calculator, then you need brackets around the 14 over 0.25. I think that's obvious. Anyway, Elaine's investment is a little bit more than Jerry's. Interest compounded more frequently, even though you get a smaller chunk of the interest regularly, accumulates to a higher amount. So the amount after 14 years is $30,311 and 65 cents. The interest would be $10,311.65. Any question about part B? How long would it take Jerry's and Elaine's investments to reach 40,000? Well, for Jerry, you're going to have 40,000 equals 10,000 times 1.08 to the T. For Elaine's investment, you're going to have 40,000 equals 10,000 times 1.02 raised to the T over 0.25. And I hope it's clear you do not know how to algebraically solve for T. We're doing a graphical approach. So we're going to graph Jerry's growth function, and we're also going to graph 40,000, which will be a horizontal line up at 40,000, obviously. We have 10K times 1.08. Didn't really need the brackets there. Could have just put times raised to the x. Raised to the x. You might go to your table to get an idea of what kind of domain we should look at, starting at 0 and going up by 1. It's going to be between 18 and 19 years. So I'm going to, in my window setting, go from 15 to 20. And for y, I need to go up to at least 40,000. I'm going to go 45,000. I should see Jerry's investment climbing. That's not the y-intercept, by the way, because I didn't start at 0. And there is the horizontal line. So the mathematical solution to this equation is 18.01 years. What is the answer to the question? It's 19 years. Because at 18 years, it hasn't reached 40,000 yet. And Jerry doesn't get interest at the 0.01 year mark. If Jerry has his heart set on that new speedboat, and he's got no other money, come the beginning of the year, he looks in the account, he doesn't have enough for it yet. Now, setting aside practicalities, like I'm sure George or Kramer could lend him a few bucks so he could buy the speedboat, he still doesn't have it until at the end of the next year. So the answer to this is 19. Be careful here. That's because it says, if you read the question, it says, how long would it take? And it doesn't really specify. If it said, round your answer to the nearest tenth, then you would say 18.0. Okay. What about Elaine's investment? Well, So this is for Jerry. What about for Elaine's? We'll just go in and edit our equation. It was 10,000, it was 1.02. This time we need a set of brackets around the exponent, t over 0.25. Looks okay, let's graph it again. You get 17.50. Okay. So this is the mathematical solution to Elaine's. What is the answer to the question?
17.7.
Right, 17.75. Because Elaine gets interest at the 0.0 mark, the 0.25 mark, the 0.50 mark, the 0.75, and back at the 0.0. So I've designed these questions here in our notes to give us numbers that, even though it's very close to 17.5, we have to bounce it up. If it was 17.49, we'd say 17.5. We've got to bounce up to the nearest quarter, which would be 17.75. These are both years. If I said to you, and I don't think I have this in your notes, but if I said, never mind. Okay. You're going to be getting a written response question probably next week dealing with investments and trying to find out where one person's investment surpasses another person's investment. Because one person starts off with less money, but their interest rate is accumulating money more frequently. Page 364, 4, 5, 7 are 4 and 5 are dealing with solving equations, so is 7. 8 through 14 are dealing with investments. I believe the answer to number 13 and 11 are wrong in the back, but if you were to look in your textbook in the back, I think somebody's probably already made that correction, because we discovered this correction a long time ago.